So good afternoon, good evening for you, Teresa. Good morning for you, sorry. This is the defense of the master thesis by Maria Teresa Corzo Lopez. You have from about 20 to 25 minutes for your defense. So you can start whenever you want.
Okay, thank you. Good afternoon. Today I'm going to present my master's thesis, that is the Inference of Leadership, Networks of Marine Megafauna from Acoustic Data. So first, in the presentation, I'm going to talk about a little bit about complex systems in animal behavior, then get more in depth with the shark's behavior, and then I will talk about two specific species of shark that are the blacktip and the gray reef shark. Finally, I will talk about the acoustic data where we obtain our information. And then I will talk about the methodology and results, the network visualization of our represented data, and the possibility of a hierarchy on these two species. And lastly, I will talk about the conclusions of the work. So first, what are complex systems in animal behavior? They are a tool to understand interactions among different factors that influence animals in their natural behavior. And we have some three key aspects that we're going to talk about. We have first the collective emergent behavior. And here complex systems help us with collective interactions that will result in unpredictable patterns. We can see these patterns, for example, in bird flocking or in school of fishes, for example. Then we have feedback loops that here we can see the animal behavior of some species to amplify this behavior or dampen the behavior, depending on the positive feedback or negative feedback that we have. And for example, we can see this in predator-prey behaviors. And finally, another aspect that we can see in complex systems in animal behavior is the nonlinearity and self-organizations, where we can see that a small change in an initial condition in the behavior can have large effects for these populations. Now, I will talk about a little bit more about the behavior of sharks as predators, as loner behavior. We know that sharks are the top predators in the marine ecosystems. They are in apex predators, and they help regulate the marine ecosystem with their predatory behavior. They tend to be loners due to the efficiency they have in order to prey and maintain the marine ecosystems. So they have more reputation of being loners, and this behavior is seen when they are very young. But even though they are usually more loners, they tend to have some social behavior, and we can see this social behavior especially in courtship and mating, where is the most important part of their social behavior. They can tend to have body language, chemical signaling among each other, and sometimes this social behavior can also be due to the cooperative hunting. That is a strategy that some species have between each other. So now we have the blacktip reef shark and the gray reef shark that are the two species that I'll be focusing in. These two species have been known for a semi-solitary behavior. This means that they do have some social behavior, and recent studies have shown that these two species tend to have these hierarchies where there are some more dominant roles and more submissive roles. So these two species are the ones that I will be focusing on this master thesis. And the data that we obtained was an acoustic type of data. And this means that all of the individuals that were detected, they have an emitter, and we have different transmitters in different stations among Australia. And these kind of transmitters detect what time they passed by, at what location, and different detection times that they had along the years. So this is the data that we will be using. It was obtained from the Integrated Marine Observing System. And in the bottom, we can see the two pictures of the data for blacktip reef shark and for gray reef shark. So we can see that there are two focal points in the east and west of Australia where we can see the stations that we studied. And for the gray reef shark, we have here 5 focal points where all of the stations that we studied are focused on. So now that we know what data we're going to work with and the species we're going to work with, what I did is that I created a leader follower network in order to understand the behavior among them. If there is a leader and a follower within all the data that we work with. So what we did is that imagine that we have two individuals, I and J. So we want to observe the behavior among them if there is a leader or a follower. So we're going to look at the so we're going to look at the times where the individual I, is detected after the individual J, or vice versa, when J is detected after I. We want to see which is the shorter time, because the shorter time will tell us who is following whom. So what we have is that we have two waiting set times, and we will apply this waiting set time, the Kolmorov-Smirnov statistic, that will help us measure how different these probability distributions are. If they are very different, we will have that one is following the other. And for this Kolmorov-Smirnov statistic, this is a non-directed attribute, so we added a narrow Kolmorov-Smirnov statistic in order to have a directed way to see this. So who is following whom, and we can see this network attribute more visual. It is important to note that we also we assigned a p-value to the interactions that were only statistic relevant. So we randomized the data in order to know which are the interactions that we find more relevant, and we only kept those interactions. But how can we quantify this kind of leadership? Because this will only tell us who is following whom, but we want to know a little bit more about this. So this is where the leadership and participation index come into play. That this will be two measurements that help us also understand a little bit more about each of the individuals of the networks. So the leadership index will measure the strength of influence exhibited by each individual node. So we'll have the in strength. The in strength is how often an individual is followed, and we will subtract the out strength. Then that the out strength is how often an individual follows others. So this will give us insight of who is in the influential node, who is more leader and who is more of a follower. Then we will have the participation index, that is the addition of the in and the out strength. And this will tell us how relevant a node is to the network. If it's if the value is lower, it means that it's not as influential because it doesn't have very relevant nodes to it. And finally, we will have the directed acyclic graphs that will help us visualize and understand if there is a hierarchy, because we can have leader and followers, but the main goal of this thesis is that we want to find if there's a hierarchy or not. So what are directed acyclic graphs? It means that they're directed graphs that doesn't have circular dependencies. So it's just like a total hierarchy. There are nodes that they don't have a circular dependencies among each other, so they don't have cycles. And this will help us identify a specific node as the leader. So now that we know what the network visualization would look like with the Kolmorov-Smirnov statistic, the leadership index, the participation index, and the measurement will be the directed acyclic graph, I will show you a little bit more of the results. So first, I plotted the distribution of individuals for both species at the top 10 stations. This means that for every station that we found at of the data, I plotted all of the tag IDs into the different stations. And we can see here a first insight of our work, that is that there's some spatial interaction among them. So for example, in the gray reef shark, if we see at the left, we can see that all of the individuals, the tag IDs for this species, for example, from 5 to 21, we can see that they are found in the same station, that is the red station. For example, this is SR4. And we can see this kind of behavior for all of the stations at the tag IDs, that they are kind of clusterized among different stations. So this gave us our first insight of what we were expecting, but we wanted to look at the social interaction among them. So what we did is that I applied the leader-follower network for each individual station, and we obtained two different kind of networks. The first kind of network is the one that we will see here, and I will explain it right now. But first, I will show you a little bit more the visual attributes that you can see in order to understand a little bit more the networks. So we can see that we have a color. This will represent the leadership index. So the bright red means a positive leadership index, and a deep blue means a more negative leadership index. So in other words, we can say that, for example, the reds are the leaders and the blue are the followers. Then we have the shape of the nodes. The shape will denote the sex of the individuals. A triangle is a female and a circle is a male. Then we have the size of the nodes. The size is the participation index. So bigger node will mean a higher participation index, and a smaller node will mean it's not as participant and like it's not as influential in the network as others. And finally, we have the width of the edges, and the width of the edges will denote the Kolmar of Smirnov distance. And as I told you, it will be an arrow, so we can see the direction of who is following whom in these individuals. So we had the first kind of network that we obtained. It was a directed acyclic graph. So we can see here for both of the networks that we have a directed acyclic graph because they are following one node to another, but we don't have any circular dependencies. So all of the following we are doing here, they don't like return to follow another one. So we can see here for both of the networks that this is applied. And with our visual attributes, we can see that, for example, for black tip reef shark, we have a higher leadership index in Clary. It means that is the leader of this network. And then for gray reef shark, we have the node 53 that we can see that is also a leader in this network, that they have the most in edges to them. So as I told you, we will have two types of graphs. This is the directed acyclic graph, and the second type of graph in different stations that we have were non-directed acyclic graph. It is important to note that out of 29 study stations for blacktip, only 6 were non-directed acyclic graphs. And for gray reef shark, we have 56 studied stations, and out of those 56, only 20 were non-directed acyclic graphs. So we can see that they are starting to tend to have a total hierarchy in most of the individual stations. So for non-directed acyclic graphs, we have here two examples, one for each species. And we have here that, for example, in blacktip reef shark, we have a circular dependencies with the node 27, 32, and 33. So even though this is a leader, we can see that there are circular dependencies among them. So we cannot say that is a total hierarchy. And for example, in gray reef shark, we have here in 52, 50, and 57. So now that we know the behavior of each of the individual stations, we want to know the overall behavior. So what we did is that out of the 29 stations of the 56 stations, I added all of the individual stations networks into a whole global aggregated network. And this will show us a little bit more of this behavior. So for blacktip reef shark, we have here the aggregated network with all of the interactions of each of the individuals from different stations, but now clusters in aggregated network. Since we added directed acyclic graphs and non-directed acyclic graphs in the individual stations, we know that for sure this is not going to be a directed acyclic graph. It will be a non-directed acyclic graph. But we know that it's a tendency of hierarchy, but how can we measure this? So what we did is that for this aggregated network that is a non-directed acyclic graph, I deleted each of the edges that were making this a non-directed acyclic graph. So I found the weakest cycle, and then for the weakest cycle, I deleted the weakest edge that is given by the Kolmar of Smirnov distance. And then again, the next cycle that I found, I deleted the weakest edge until this aggregated network became a directed acyclic graph. So in here we can see this process, At the top, we have the deleted edges visualized in red, and in the bottom, we can see the final aggregated network becoming a directed acyclic graph. So for black tip, for example, we deleted 141 edges. But how can we compare this if it's a small value, a small amount of broken edges, or is a normal amount of broken edges? We needed another comparison method. So what I did is that I took the original aggregated network, and I randomized this network. So this means that we have the same amount of nodes and interactions, but randomized it, not given by a social interaction. So I randomized this network, and what I did is that I also deleted the edges in the same process as I deleted this one. So I did this for 1,000 random networks, and the average of broken edges for black tip reef shark in random networks was 383.36 broken edges. So we can see in the graph that we have here the 1,000 iterations and the different broken edges that we have and the average. And we are comparing it with the red line that is the broken edges of our original aggregated network. So we can see that there is a huge difference. We can see that the that the aggregated network is very it needed a little edges in order to become a directed acyclic graph, while the random networks needed a lot more than 200 in average, more broken edges in order to become a directed acyclic graph. I did the same for the gray reef shark. And in here we can see again the broken edges that we did. For gray reef shark, we have 112 broken edges, and we can see the representation here in red. So these are the broken edges that we needed in order to this whole aggregated network to become a DAG. And then again, what I did is that I randomized this network in order to break the edges and compare it. So for gray reef shark, we had an average of 345.58 broken edges compared to the 112 from the original one. So we can see again that there is a huge gap between them. So we can see that these two networks, they do tend to have a hierarchical structure. Even though we cannot say that it's a total hierarchy, we see that they are displaying a highly structure of this. So for the conclusions of the work, we have that even though sharks are usually perceived with a solitary behavior, we can conclude that for the gray reef shark and the black tip reef shark, they do tend to have a social interaction. Also, we can conclude that in order to have a directed acyclic graph in this data set, we needed only 141 edges for black tip and 112 edges for gray reef shark, which means that they display a highly hierarchical structure, that it was the main point, focus point of our study. We also can conclude that the social behavior of these species was observed at the beginning with this spatial interaction among them in the distribution of the stations. And finally, we can, if we want to further this work and be more in depth with this work, we recommend, for example, for some future work, to compare the leadership index that was our main point with some attributes of the network. For example, maybe the sex of the network, or compare the leadership index with the participation index, or with the measurements of the species. But it's just like to get more in depth of what we concluded here, that is that we have a highly hierarchical structure for these two species. So thank you.